Properties of acids. Acids have pH values of below 7, have a sour taste when edible, and are corrosive. Acids are substances that can neutralize a base, forming a salt and water. When acids are added to water, they form positively charged hydrogen ions H+. The presence of H+ ions is what makes a solution acidic. Example: hydrochloric acid, HCl Aq, right pointing arrow H+, Aq plus Cl Aq. Typical reactions of acids. Acids and metals. Only metals above hydrogen in the reactivity series will react with dilute acids. When acids react with metals, they form a salt and hydrogen gas. Acid plus metal, right pointing arrow, salt plus hydrogen. The name of the salt is related to the name of the acid used, as it depends on the anion within the acid. Examples of the names of salts from specific acids and metals are: acids with bases. Metal oxides and metal hydroxides, alkalis, can act as bases. When they react with acid, a neutralization reaction occurs. In all acid-base neutralization reactions, salt and water are produced. Acid plus base, right pointing arrow, salt plus water. Examples of reactions between acids and bases. Acids with metal carbonates. Acids will react with metal carbonates to form the corresponding metal salt, carbon dioxide and water. Acid plus metal carbonate, right pointing arrow, salt plus carbon dioxide plus water. Examples of reactions between acids and carbonates. Indicators. Two-color indicators are used to distinguish between acids and alkalis. Many plants contain substances that can act as indicators, and the most common one is litmus, which is extracted from lichens. Synthetic indicators are organic compounds that are sensitive to changes in acidity and appear different colors in acids and alkalis. Thymolphthalane and methyl orange are synthetic indicators frequently used in acid-alkali titrations. Two-color indicators table. Synthetic indicators are used to show the endpoint in titrations, as they have a very sharp change of color when an acid has been neutralized by alkali and vice versa. Litmus is not suitable for titrations as the color change is not sharp and it goes through a purple transition color in neutral solutions, making it difficult to determine an endpoint. Litmus is very useful as an indicator paper and comes in red and blue versions, for dipping into solutions or testing gases. Properties of bases and alkalis. Bases have pH values of above 7. A base which is water-soluble is referred to as an alkali. In basic, alkaline conditions, red litmus paper turns blue, methyl orange indicator turns yellow, and thymolphthalane indicator turns blue. Bases are substances which can neutralize an acid, forming a salt and water. Bases are usually oxides or hydroxides of metals. When alkalis are added to water, they form negative hydroxide ions, OH. The presence of the OH ions is what makes the aqueous solution an alkali. Example: sodium hydroxide, NaOH, right pointing arrow, Na plus Aq plus O, Aq. Typical reactions of bases. Bases and acids. When bases react with an acid, a neutralization reaction occurs. Acids and bases react together in a neutralization reaction and produce a salt and water. Acid plus base, right pointing arrow, salt plus water. Examples of reaction between bases and acids. Alkalis and ammonium salts. Ammonium salts undergo decomposition when warmed with an alkali. Even though ammonia is itself a weak base, it is very volatile and can easily be displaced from the salt by another alkali. A salt, water and ammonia are produced. Example: NH4Cl plus NaOH, right pointing arrow, NaCl plus H2O plus NH3. This reaction is used as a chemical test to confirm the presence of the ammonium ion, NH4+. Alkali is added to the substance with gentle warming, followed by the test for ammonia gas using damp red litmus paper. The damp litmus paper will turn from red to blue if ammonia is present. Neutralization reactions. When acids are added to water, they form positively charged hydrogen ions, H+. The presence of H+ ions is what makes a solution acidic. When alkalis are added to water, they form negative hydroxide ions, OH. The presence of the OH ions is what makes the aqueous solution an alkali. The pH scale is a numerical scale which is used to show how acidic or alkaline a solution is. In other words, it is a measure of the amount of ions present in the solution. A neutralization reaction occurs when an acid reacts with an alkali. When these substances react together in a neutralization reaction, the H+ ions react with the OH ions to produce water. For example, when hydrochloric acid is neutralized, a sodium chloride and water are produced. The net ionic equation of acid-alkali neutralizations, and what leads to a neutral solution, since water has a pH of 7, is H++ OH2O. Exam tip. Not all reactions of acids are neutralizations. For example, when a metal reacts with an acid, although a salt is produced, there is no water formed, so it does not fit the definition of neutralization. Hydrogen ion concentration and pH. The pH scale. The pH scale is a numerical scale which is used to show how acidic or alkaline a solution is. It goes from 1 to 14. Extremely acidic substances can have values of below 1. All acids have pH values of below 7, all alkalis have pH values of above 7. The lower the pH, then the more acidic the solution is. The higher the pH, then the more alkaline the solution is. A solution with a pH of 7, such as water, is described as being neutral. The pH scale showing acidity, neutrality, and alkalinity. We have already seen that acids are substances that contain hydrogen ions in solution. The more hydrogen ions, the stronger the acid, but the lower the pH. The higher the concentration of hydroxide ions in a solution, the higher the pH. So pH is a measure of the concentration of H+ ions in solution, but they have an inverse relationship. The pH scale is logarithmic, meaning that each change of 1 on the scale represents a change in concentration by a factor of 10. Therefore, an acid with a pH of 3 has 10 times the concentration of H+ ions than an acid of pH 4. An acid with a pH of 2 has 10 x 10 equals 100 times the concentration of H+ ions than an acid with a pH of 4. Exam tip. Acid strength is reflected in how many hydrogen ions are in solution. The more hydrogen ions, the lower the pH, and vice versa. Universal indicator. Universal indicator is a mixture of different indicators which is used to measure the pH. A drop is added to the solution and the color is matched with a color chart which indicates the pH which matches specific colors. The pH scale with the universal indicator colors which can be used to determine the pH of a solution. Proton transfer, strong and weak acids. Extended. Proton transfer. The earlier definition of an acid and a base can be extended. In terms of proton transfer, we can further define each substance in how they interact with protons. Acids. Acids are proton donors as they ionize in solution producing protons, which are H+ ions. These H+ ions make the aqueous solution acidic. Bases. Bases are proton acceptors as they accept the protons which are donated by the acid. Diagram showing the role of acids and bases in the transfer of protons. Here water acts as a base as it accepts a proton. Strong acids. Acids can be either strong or weak, depending on how many H+ ions they produce when dissolved in water. Strong acids completely dissociate, or ionize, in water, producing solutions of a very low pH. Strong acids include HCl and H2SO4. Example of a strong acid: hydrochloric acid. HCl, AQ, right pointing arrow H plus AQ plus Cl, AQ. Weak acids. Weak acids partially dissociate, or ionize, in water and produce pH values which are closer to the middle of the pH scale, whilst still being below 7. Weak acids include organic acids such as ethanoic acid, CH3COOH. For weak acids, there is usually an equilibrium set up between the molecules and their ions once they have been added to water. Example of a weak acid: propanoic acid. CH3CH2COOH, rightwards harpoon over leftwards harpoon H++ CH3CH2COO. The equilibrium lies to the left, indicating a high concentration of intact acid molecules, with a low concentration of H+ ions in the solution. Effect of concentration on strong and weak acids. A concentrated solution of an acid is one that contains a higher number of acid molecules per cubic decimeter of solution. It does not necessarily mean that the acid is strong though, as it may be made from a weak acid which does not dissociate completely. For example, a dilute solution of HCl will be more acidic than a concentrated solution of ethanoic acid, since most of the HCl molecules dissociate but very few of the CH3COOH do. Classifying oxides. Oxides are compounds made from one or more atoms of oxygen combined with one other element. Examples of oxides include MgO, ZnO, K2O, Colorado-2, SO2, H2O. Oxides can be classified based on their acid-base characteristics. Acid and basic oxides. Acidic and basic oxides have different properties and values of pH. The difference in their pH stems from whether they are bonded to a metal or a non-metal element. The metallic character of the element influences the acidic or basic behavior of the molecule. Metals form basic oxides while non-metals form acidic oxides. Acidic oxides. Acidic oxides are formed when a non-metal element combines with oxygen. They react with bases to form a salt and water. When dissolved in water, they produce an acidic solution with a low pH. Common examples include CO2, SO2, NO2, and CO2. Basic oxides. Basic oxides are formed when a metal element combines with oxygen. They react with acids to form a salt and water. When dissolved in water, they produce a basic solution with a high pH. Common examples include CuO and SaO. Amphoteric oxides. Extended. Neutral oxides. Some oxides do not react with either acids or bases and thus are said to be neutral. Examples include N2O, NO, and CO. Amphoteric oxides. Amphoteric oxides are a curious group of oxides that can behave as both acidic and basic, depending on whether the other reactant is an acid or a base. In both cases, salt and water are formed. Two of the most common amphoteric oxides are zinc oxide, ZNO, and aluminum oxide, Al2O3. The hydroxides of both of these elements also behave amphoterically. Example of aluminium oxide behaving as a base. Al2O3 plus 6HCl right pointing arrow 2AlCl3 plus 3H2O. Example of aluminium oxide behaving as an acid. Al2O3 plus 2NaOH right pointing arrow 2NaAlO2 plus H2O. This acidic and basic behavior is not easily explained by donating or accepting protons. A separate theory called the Lewis acid-base theory can identify acids or bases in these situations, but is not required for this course. Preparing soluble salts. Salts. A salt is a compound that is formed when the hydrogen atom in an acid is replaced by a metal. For example, if we replace the H in HCl with a potassium atom, then the salt potassium chloride is formed, KCl. Salts are an important branch of chemistry due to the varied and important uses of this class of compounds. These uses include fertilizers, batteries, cleaning products, healthcare products, and fungicides. Naming salts. The name of salt has two parts. The first part comes from the metal oxide or metal carbonate used in the reaction. The second part comes from the acid. The name of the salt can be determined by looking at the reactants. For example, hydrochloric acid always produces salts that end in chloride and contain the chloride ion, Cl. Other examples. Sodium hydroxide reacts with hydrochloric acid to produce sodium chloride. Zinc oxide reacts with sulfuric acid to produce zinc sulfate. Preparing salts. Some salts can be extracted by mining, but others need to be prepared in the laboratory. The method used depends on the solubility of the salt being prepared. Preparing soluble salts. Method A. Adding acid to a solid metal, insoluble base or insoluble carbonate. Diagram showing the preparation of soluble salts. Method. Add dilute acid into a beaker and heat using a Bunsen burner flame. Add the insoluble metal, base or carbonate, a little at a time, to the warm dilute acid and stir until the base is in excess, i.e. until the base stops disappearing and a suspension of the base forms in the acid. Filter the mixture into an evaporating basin to remove the excess base. Heat the solution to evaporate water and to make the solution saturated. Check the solution is saturated by dipping a cold glass rod into the solution and seeing if crystals form on the end. Leave the filtrate in a warm place to dry and crystallize. Decant excess solution and allow crystals to dry or blot to dry with filter paper. Example: preparation of pure, hydrated copper 2 sulfate crystals using method A. Acid equals dilute sulfuric acid. Insoluble base equals copper 2 oxide. Method: add dilute sulfuric acid into a beaker and heat using a Bunsen burner flame. Add copper 2 oxide, insoluble base, a little at a time to the warm dilute sulfuric acid and stir until the copper 2 oxide is in excess, stops disappearing. Filter the mixture into an evaporating basin to remove the excess copper 2 oxide. Leave the filtrate in a warm place to dry and crystallize. Decant excess solution. Blot crystals dry with filter paper. Equation of reaction. Copper 2 oxide plus sulfuric acid right pointing arrow copper 2 sulfate plus water. CuO(S) plus H2SO4 Aq right pointing arrow CuSO4 Aq plus H2O(L). Method B. Reacting a dilute acid and alkali soluble base. Diagram showing the apparatus needed to prepare a salt by titration. Method. Use a pipette to measure the alkali into a conical flask and add a few drops of indicator thymolphthalane or methyl orange. Add the acid into the burette. Record the starting volume of acid in the burette. Add the acid very slowly from the burette to the conical flask until the indicator changes to the appropriate color. Record the final volume of acid in the burette. Calculate the volume of acid added. Final volume of acid, initial volume of acid. Add this same volume of acid to the same volume of alkali without the indicator. Heat the resulting solution in an evaporating basin to partially evaporate, leaving a saturated solution, crystals just forming on the sides of the basin or on a glass rod dipped in and then removed. Leave to crystallize, decant excess solution and allow crystals to dry. Preparing insoluble salts. Extended. Insoluble salts can be prepared using a precipitation reaction. The solid salt obtained is the precipitate, thus in order to successfully use this method the solid salt being formed must be insoluble in water, and the reactants must be soluble. Using two soluble reactants. Diagram showing the filtration of the mixture to remove the precipitate. Method. Dissolve soluble salts in water and mix together using a stirring rod in a beaker. Filter to remove precipitate from mixture. Wash the residue with distilled water to remove traces of other solutions. Leave in an oven to dry. Example, preparation of pure, dry lead-2-sulfate crystals using a precipitation reaction. Soluble salt 1 equals lead-2 nitrate. Soluble salt 2 equals potassium sulfate. Method. Dissolve lead-2 nitrate and potassium sulfate in water and mix together using a stirring rod in a beaker. Filter to remove precipitate from mixture. Wash precipitate with distilled water to remove traces of potassium nitrate solution. Leave in an oven to dry. Equation of reaction. Lead-2 nitrate plus potassium sulfate, right pointing arrow, lead-2 sulfate plus potassium nitrate. Pb NO3 2Aq plus K2SO4 Aq, right pointing arrow, PbSO4 S plus 2 KNO3 Aq. Solubility rules. Salts are prepared by different methods, depending on whether the salt is soluble or insoluble, so it is important to know the solubility of salts. Solubility of the common salts. Hydrated and anhydrous salts. When salts are being prepared, some water can be retained within the structure of the salt during the crystallization process. This affects the crystal's shape and color. Salts that contain water within their structure are called hydrated salts. Anhydrous salts are those that contain no water in their structure. A common example is copper-2 sulfate, which crystallizes forming the salt hydrated copper-2 sulfate, which is blue. When it is heated, the water from its structure is removed, forming anhydrous copper-2 sulfate, which is white. The hydrated salt has been dehydrated to form the anhydrous salt. This reaction can be reversed by adding water to anhydrous copper-2 sulfate. Hydrated copper-2 sulfate rightwards harpoon over leftwards harpoon anhydrous copper-2 sulfate plus water. Water of crystallization. Extended. Water molecules included in the structure of some salts during the crystallization process are known as water of crystallization. A compound that contains water of crystallization is called a hydrated compound. When writing the chemical formula of hydrated compounds, the water of crystallization is separated from the main formula by a dot. E.g., hydrated copper-2 sulfate is CuSO4 bullet operator 5H2O. Hydrated cobalt-2 chloride is CoCl2 bullet operator 6H2O. The formula shows the number of moles of water contained within 1 mole of the hydrated salt. E.g., hydrated copper-2 sulfate, CuSO4 bullet operator 5H2O, contains 5 moles of water in 1 mole of hydrated salt. A compound which doesn't contain water of crystallization is called an anhydrous compound. E.g., anhydrous copper-2 sulfate is CuSO4. Anhydrous cobalt-2 chloride is CoCl2. The conversion of anhydrous compounds to hydrated compounds is reversible by heating the hydrated salt. Anhydrous to hydrated salt. CuSO4 plus 5H2O, right pointing arrow, CuSO4 bullet operator 5H2O. Hydrated to anhydrous salt by heating. CuSO4 bullet operator 5H2O, right pointing arrow, CuSO4 plus 5H2O. Diagram showing the dehydration of hydrated copper-2 sulfate.